In this problem we have a function h. We're not told what the function h is, but we're given some values for h when x is 1, 2, and 3, and we have some values for the first derivative, second derivative, third derivative, and fourth derivative of h at x equals 1, 2, and 3 as well. Now we're also told in addition to that that the function and the four derivatives are all increasing on the interval, and that's going to turn out to be important information, and we'll see how to use that in part A. Part A, we want to write the first degree Taylor polynomial for h about x equals 2 and use it to approximate h of 1.9. So here's something that we need to remember. The general form of a Taylor polynomial is the sum from n equals 0 to infinity of the nth derivative of f evaluated at the center divided by n factorial times x minus a, again the center, to the nth power. And so your Taylor polynomial is just a string of these terms constructed in this way. And here we want to find the first degree Taylor polynomial for h about x equals 2. And the first degree Taylor polynomial, in general, it's going to be, there is no zeroth derivative, that's the original function. So it's the original function evaluated at the center over 0 factorial, which is 1, and x minus a to the 0 power, which is also 1. Then plus f prime, the first derivative, evaluated at the center, divided by 1 factorial, which is still 1, times x minus a, the center, to the first power. And that is the general form of the first degree Taylor polynomial for some function f. One thing you should note is this is also the equation of the tangent line. Tangent lines, in essence, are just the first degree Taylor polynomial of any function at a particular point. Alright, so in this case we're looking to use the first degree Taylor polynomial to approximate the value of the function at 1.9. So we can say that h of 1.9 is roughly equal to the value of the Taylor polynomial at 1.9, which is the original function h evaluated at the center 2 plus the first derivative of h evaluated at the center times x, which in this case is 1.9, minus the center, which is 2. And we're just going to go up to the table above to get some of this information. H of 2 is 80 plus h prime of 2, that is 128. 1.9 minus 2 is negative 0.1, and we get from this 80 minus 12.8, which is 67.2. So that is the approximation of h of 1.9 using the first degree Taylor polynomial for h about x equals 2. Then the question asks, is this approximation greater than or less than h of 1.9? And explain your reasoning. Well, this is where the information that we're given above comes in very useful. It says that the function and all of these derivatives are increasing on the interval from 1 to 3. So, if the function is increasing and the first derivative is increasing, then we have a concave up segment that looks something like this. and any tangent line drawn to a concave up segment is going to under approximate for all values other than the point of tangency. So we can state it this way: t sub 1 of 1.9 is less than h of 1.9 since h of x, h prime of x are both increasing on x greater than or equal to 1, less than or equal to 3. And that's good enough. We'll know that it will be an under approximation, and we've explained our reasoning. We'll go on to the second part in the next video, part B.